Hello and welcome to the Theory of Computation lectures. In this class, we will discuss some more problems on DFA. So the first problem that we'll take is to make a DFA over input alphabet of 0 and 1 to accept strings containing substring 0, 1. Now, when it is said that all the strings should contain a substring 0, 1, that means 0, 1 could occur in the beginning of the string, it could occur in the end of the string, it could occur in the middle of the string, as long as the string contains 0 and 1 contiguously, that string should be accepted. So as you can see in the example of the language that is to be accepted by the machine, 0, 1 could occur in the beginning of the string as in these cases, or it could occur in the end of the string as in these cases, or it could also occur in the middle of the string. So the machine should accept all such strings. Okay. As before, we start by designing a machine which will accept the smallest possible string in the language, which is 0, 1. So let's start by designing a machine which accepts 0, 1. So we start from initial state A. As soon as I get a 0, I go from A to B, and then as soon as I get a 1 in B, I go to the final state C. So this machine now accepts the smallest possible string in our language. Let's complete the machine. So in state A, if I get 0, I go to state B. What if I get a 1 in state A? So that means the first symbol that I come across is 1, which is similar to a case like this here. Now if I get a 1 initially, I should wait in state A, isn't it? I should keep waiting in state A till I get a 0 so that I could go to B. So as I get 1 in state A, I will keep waiting in state A. Now let's look at state B, and what if I get a 0 in state B? Now I am in state B, that means the last symbol that I encountered was 0. So if I get another 0, I should keep waiting in state B, because as soon as I get a 1, I will go to state C. So if I get a 0 in state B, I will keep waiting there, because as soon as I get a 1 after that, I can go to the final state. Now how can I complete the final state? Let's think. Okay, so if I have come to state C, that means I have already seen a substring 0, 1 in the string. So after that, whatever comes doesn't really matter, because our string will always contain the substring 0, 1. So in state C, either we get a 1 or a 0, we will continue to remain in state C. So what are the observations on this design? First of all, we see that the dead state is not required. Secondly, there is a loop in the final state. Thirdly, the length of the substring being 2, the number of states required were 3. So in this case, the number of states required were 1 more than the length of the substring contained. Let's do another problem which is similar to this. So this time we have to accept all strings containing substring 100. So again, the language will contain 100 as a substring. It could occur in the beginning of the string, it could occur in the end of the string, or in the middle of the string. So the smallest possible string in the language is 100. Let us first design a machine to accept that string. So we start from an initial state A. From A, if we get a 1, we'll go to state B. From B, if we get a 0, we go to state C. And from C, if we get a 0, we go to state F. Now let's complete the machine. Now in state A, if I get a 0, as before, we will continue to wait in state A. In state B, if we get a 1, we should continue to wait in state B. What if we get a 1 in state C? So if we get a 1 in state C, that means I have got 1, 0, 1. Now if I have got 1, 0, 1, that means the substring 100 can occur only if we get another couple of zeros after this, right? So we have got 101, we can get 2 more zeros and still have the substring in our string. So which is the state from which if we get 2 more zeros, we can go to the final state? That state is B. So from state C, if we get a 1, we should go to state B, so that if we get 2 more zeros after that, we can still reach the final state. Now once we have reached the final state, as we have seen in the previous case, irrespective of whatever we get after this, the string will always contain the required substring 100. Hence, there will be a loop in the final state. Now, again, the observations are that dead state is not required in this case. Loop in the final state. the length of the substring being 3, we needed 4 states. So in general, if you are asked in your question to design a DFA which contains a substring of length n, then you should understand that your DFA will be containing of n plus 1 states. And also these 2 points are important, that in such cases there will be no dead state and there will be a loop in the final state. Okay. Now let's look at a different problem. In this case, we are asked to design a DFA over the input alphabet 0, 1 to accept strings starting and ending with the same symbol. Notice that they are telling us to design a DFA which start and end with the same symbol, but they are not telling us which symbol is it. This means that if the string starts with 0, it should also end with 0. And if the string starts with 1, it should end with 1 as well. So now let us ask ourselves if a single 0 or a single 1 is to be accepted by our machine. So notice this, if the string contains only one 0, it starts with 0 as well as ends with 0. So it should be accepted by the machine. Similarly, a machine should accept a single 1 because the string starts and ends with the same symbol 1. So the language should contain 0, 1 and then 0, 0, 1, 1 and other strings like 0, 1, 0, 1, 0, 1, etc. So what is the smallest possible string that is accepted by our machine? It is either 0 or 1. So we begin by designing the machine by starting from an initial state A, and then from A, if we get a 0, we reach a final state B, and if we get a 1, we reach a final state C. So there are 2 final states in this machine. Now in state B, if we get a 0, that means the string is starting with 0 and we get more zeros, that means it ends with 0 as well. So we will continue to remain in state B as long as we get 0. Similarly, we will continue to remain in state C as long as we get 1s. Now in state B, if we get a 1, we go to another state, which is state D. This is not a final state, you see, because in state B, if we get 1, that means the string started with 0 and has now ended with 1. So that string should not be accepted. So as long as we get a 1 in state D, we will continue to remain in state D. But as soon as we get a 0, we go back to state B because now the string becomes acceptable. It has now started and ended with the same symbol 0. Similarly, from state C, if I get a 0, we go to a state E, which is not a final state because the string has started with 1 and the last symbol encountered is 0. And as long as we get 0, we will continue to remain in state E. But as soon as we get a 1 in state E, we will go back to the final state C. So that completes the design of a DFA which accepts all strings that start and end with the same symbol. A similar problem asks us to implement a DFA that accepts strings starting and ending with a different symbol. So if the string starts with 0, it should end with 1, and if it starts with 1, it should end with 0. So the language should contain strings like 0, 1, 1, 0 or 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0 and so on. Notice in all these cases, the strings start and end with a different symbol. So let us design our DFA by making it accept the smallest possible strings in the language. The smallest possible strings in the language are 0, 1 and 1, 0. So we start from an initial state A. In A, if I get a 0, I go to B, and in A, if I get a 1, I go to C. In B, if I get 1, I go to a final state D, and in C, if I get 0, I go to a final state E. So from A, if I reach D, that means I have received the string 0, 1, and from A, if I reach E, that means I have received the string 1, 0. Now as long as I get a 0 in state B, I can continue to remain there because after that, if I get a single 1, I can reach the final state. Similarly, as long as I get a 1 in state C, I can continue to remain in state C because after that, if we get a 0, we can go to the final state E. Now in state D, if we get 1, we should remain there because, that means the string started with 0 and the last symbol that we have seen is 1. That means it has started and ended with a different symbol, which is an accepting criteria. So we should continue to remain in the final state. But if we get a 0 in state D, we should come back to state B because then the string has started with 0 and the last symbol seen is also 0. That should mean that the string does not remain in the final state D and it comes back to state B because after this, if we get a 1, we can still go back to the final state D and accept the string. And similarly in state E, if we get a 0, we will continue to remain in state E, and if we get a 1, we will go back to state C. So that concludes the design of a DFA which start and end with a different symbol. In the next class, we will talk about some more design of DFAs. Thank you very much.